We will be starting a new topic, okay, and that topic is more related to the health effects of the pollutants. See, if you recall, we began with a very three components, like STR, source, transport, receptor. And then we said the basic objective was to safeguard the receptor and then decide as to what should be the source emissions could be allowed and how the transport mechanism and all. So we have been so far studying the transport, or not transport, but the transformation, largely the atmospheric chemistry. Okay, now we want to quickly and briefly, but still capturing the important points of health effects. We are not the medical people, nor we want to be the medical experts, but we should understand what the doctor can talk and what the health effects really mean to us. Okay, so if you recall, this is something which we have talked several times: large particles, small particles, PM10, PM2.5, and ultrafine particles. Okay, you will also see as the particle size decreases, the impact or the implication in terms of health effects goes up for two reasons, both physical reason as well as the chemical reason. Okay, because you see, when the particle becomes small, okay, its surface area becomes very large, and surface area large is going to absorb lots of toxic compounds, which may be the organic compounds, the metals. So as a result, as you go the smaller the particle size, then you have the problem. And also you will see the smaller particles, this and this, will penetrate deeper in the lungs. Okay, so while the bigger particles will be stopped at the nasal entry or at the upper part of your respiratory system, and then you sneeze, and the body has n number of mechanisms, because lung is such a vital organ. But unfortunately, the particles go very deep. Okay, these particles are not able to come out, and it can cause serious problems. We'll see how it happens. But you can see again, from the health point of view, we looked at the formation point of view, if you recall, in the class. But here we say, even from the health point of view, the smaller particles are of a greater significance. Okay, if you look at the Indian conditions, for example, okay, we will a little bit focus on particulate matter more than the gaseous. You see here, this is the little old picture that we have, like of 1999. But things haven't changed so much. So you see, when you are talking about the SPM, so SPM is high, it means by and large the PM10 will be high, PM2.5 will be high. The four different cities, and this is what is about the annual standard, as you see here, about 160 or something. And pollution levels are way high. Okay, the gaseous are, well, still manageable, but the associated problems we'll discuss a little later, but the particulates are important to us. So this lecture will devote more onto the particle health effects. Okay, before I explain more, this is all established in the literature, but that we don't have to cover in this course, that it changes, or not only changes, but increase the particulate pollution, okay, increase the mortality. Okay, it has been documented, researched, published, and established, if I can use that word, that more people die in more area which is pollution area, both in terms of the annual as well as if there is a daily variability in the particulate pollution, the mortality people have shown the increase in mortality. So is in the hospital admission, respiratory symptoms, moderate or the worst asthma status, like a person is asthmatic, it can trigger asthmatic attack. Okay, change in the pulmonary functions you can take as the lung function. Okay, days of work loss, efficiency goes down, and things like that. So these are the issues, the broader issues, but we need to get a little bit more specific. And the target organ, the main target organ for the air pollutants is lungs. Other things also happen, but largely it is the lungs, and which is the very, very important this thing. So these are the nasal cavity you have, and this is what is the larynx you have. You have carina, this is the lungs, this is the diaphragm, which is like a pump which kind of pushes back and forth your lung, this thing, and then this is this is a trachea, and then it's not being shown, but the left hand side there will be bronchial, left bronchial and the right bronchial, and the other further breakdown and further classification as to what happens. That will become a little clear in the next picture, but before that you can also see how the particles, what kind of particles would be stopped at what place. Okay, the larger particles, like 7 to 11 micron, they would be stopped somewhere here, but once you come to the stage 2, these particles of like less than 10, they're likely to stay at the trachea level, and this is stage 3. This is upper trachea and primary bronchial. This is primary bronchial, and then you have the secondary bronchial, which could be left bronchial or the right bronchial, and then you see this particle range, which is coming about 2.1 to 3.3, and the ultrafine particles, you see it's going very, very deep, almost at the place where the actual oxygen transfer takes place. And we'll show you a little picture of this thing as to how it looks like. We are with the light system as we have here. So if you see here, if you take the lung portion bigger, okay, then this you can take as a bronchial. Okay, this here standing, this will be the left bronchial, and then finally something which terminates into the smaller, like this structure. This is called the terminal bronchi. So you can't read in the back, but this is like the terminal bronchi, because after that there will be no more bronchi. Okay, this is called the terminal bronchi. And then you see at the end, what it ends is really like, it's called sacs, S-A-C-K-S. Okay, and they are little, you can really see this like the bunch of grapes. Okay, and it provides a lot of surface area. Okay, and if you bring it a little bit, try to look from inside, you see these are really filled by the air as you breathe. Okay, and these things have a lot of elasticity. Okay, a lot of elasticity. So as the the lungs are filled with the air, as you can see, and this is a membrane. The other side has all your blood streams are there. Okay, which will carry the blood. So what happens? So if you have something like this is filled with air, and this side are the approximately your blood carrying, not the arteries, but blood vessels. So here you have the oxygen and plus something pollutant or whatever. See, the partial pressure of the oxygen is way high onto this side. So as a result, and the partial pressure of CO2 is very high on this side. So CO2 will exchange because and this is a membrane, don't forget. This is a membrane. So your CO2 will transfer from the blood into the lungs, and the oxygen from the lungs will go to this side. So this goes on to this side. Okay, so this exchange takes place. So we are talking about these things, and then you can see the fine particles which can come here, which in fact they do come. Okay, the kind of path which they go through, the treacherous path. Okay, it's very unlikely that once they get deposited, okay, because and then there's no mechanism through which they can be taken out. They will stay there for quite some time. Okay, or they stay there in fact permanently, because the upper part, okay, you sneeze and all the dirt from here will come out. There's also body has a mechanism to clean the things even from this region. Okay, we'll see how it does. But then if things go deeper, okay, and get deposited, okay, they will be damaging the tissues here, and once these tissues are damaged, almost there is no possibility of recovering the things. One is the aging process, people suffer, and then somehow what really happens when tissues are dead, it loses its elasticity. And once it loses elasticity, it is kind of like it cannot maintain the partial pressure. So the exchange of both oxygen as well as the CO2 is affected. So both happens because of the pollution as well as the aging process. So you can see if the person is old and he's in polluted area, see as it is, because of the aging process he has a difficulty, and then exposed to the higher pollution level. So you can see how it kind of cause the problem. So older people will have the problem, and there's no way these can be regenerated. But fortunately in the body these are millions of sacs. Okay, sacs is like a pocket. Okay, so millions and billions of sacs are there, but then they get damaged. Okay, but if the particle which is not deposited somehow, there is also the possibility that that particle can go back, because we are talking very fine particles with almost insignificant inertia. Okay, so this is what is the, we are not the doctors, we are not going into deep things, but still we should know about these things. Okay, like let's look at the upper respiratory part of the lung, not at the end, but at the upper part. You see here, this is the it flows through this one, the air. It has a little hairy structure. Okay, see here, hairy structure. If you take the blow up picture of this one, it looks like this. Okay, and this hairy thing is called cilia. Okay, and in addition to cilia, there is a mucus, which is called mucus layer. There is a mucus, okay, which sometimes you sneeze, that is basically mucus that is coming out. That is also secreted. Okay, that is there, and this, and the particles will, because it's a wet surface, so it is on the upper part. Lower part, if you have the at this point, if you have the wet surface, I think the person will die. Okay, so that's where we just want the gases there. But in the upper part, we have the mucus and mucus layer, and the body, the moment the particles are there, more mucus is released. And the cilia, as you see them, they are constantly like waving in the lungs. Okay, and once they are waving, so the particles comes, and then it kind of really pushing them little up. Okay, and once it pushed them up, okay, you have little cilia here, the upper part, then the lower part is somewhere here. So in fact this mucus layer, okay, where the particles will be trapped, this travels against the gravity. So cilia is cleaning the things, and what are the particles that are trapped, which are the little larger particles, 3 micron or so, they will be traveling along with the mucus. Okay, same on the right side. Okay, and then this is your food pipe. Okay, bad drawing, but well, and then this will almost all the dirt. Okay, this will reach up to here. Okay, and then you swallow the things. So all the dirt which was affecting the lungs go back into your food pipe. These things. Okay, so this in fact, this mechanism, it's called spelling you have to check, mucociliary elevator actually. It's like a lift, if you like it. So it's like a lift which kind of is lifting the things against the gravity. See the body mechanism and all the particles which are there. So the upper particles in the upper part of the lungs, things can be taken care of. But we go to the deeper part, I mean these mechanisms are not so good. So the small particles are of great significance. Okay. There's a little, you'll need a little understand some terminologies, and don't worry, I'll pass on these things to you. You can have a look onto this one. This is, suppose on this side, okay, I'm plotting the percentage of the total lung capacity, okay, from 0 to 100, okay, and as you normally breathe, okay, normal at rest you are breathing, this is how you are breathing, in, out, in, out, in, out, okay. Suppose if I ask you, okay, that, well, take as much breath as you can, okay. Okay, this is what is it. Now this person is asked to take a deep breath, and he can almost fill all his lungs with the entire air that he can. Okay, then I ask him to please exhale as much as you can. Okay, okay. So this capacity, okay, is called the vital capacity. Okay, no matter how much he tries, this amount of the air, or this volume of the air, he cannot exhale. So that is called as a residual volume. Okay. That kind of volume is always present in the lungs. Okay. So this thing, okay, the total capacity minus the residual capacity is called the vital capacity. Why vital? It is vital because from the operational point of view, this is vital. This is not, we can't use so much about this one. So this is what we call as the vital capacity. Okay, and then again this I can transfer in the volume units basically. Okay, so this is what is measured in the volume. So I don't think I have the numbers here, but how do we write here? This is a little higher. Okay, this was pointed out by the doctors to me. This is generally the male will have about 5,000 ml. This is really high. So 5,000 ml, okay, and females will have about 3,500 or so. Okay, so you can see that that is your total lung capacity. Okay, this is also the taken as a vital capacity that is in there. So now what the, and this which is a normal capacity what you are taking in the volume in and out, that is called the tidal volume. Why? Because it's a tidal process that you go up and down, up and down. Okay, and now you see here, suppose from this point, okay, this point, okay, you have to little be careful here, that from this point, okay, if I ask person, okay, to exhale out, okay, as much air as possible, okay. So basically from here, so if this point is same as this one, okay, I ask him to exhale, okay, maximum that he can exhale is because I mean let's see, okay, we are here, okay, and maximum as a normal operation, maximum that he can exhale is this volume, right, from the normal operation. That is called expiratory, because you are expiring, expiratory reserve volume. Okay, so it means what really it indicates is, suppose you are feeling very suffocated and something polluted air has gone. So how quickly and how much you can exhale out. So that is called the expiratory from your normal level that you have expired. So this is the level. Okay, inspired one, inspiratory from normal I have taken, and then again I want to take. So this is normal. See this is see. And then go beyond that. That is called the inspiratory reserve volume. Okay, this volume is also very important, and that again lung capacity and something. Suppose you want to go in a smoky area and still want to do something. You see the smoke and you want to go and put off the stove somewhere. Okay, then what you will do, if you have good inspiratory volume, then go there, don't inhale or exhale, store, reserve it, because this is a reserve volume, okay, and then quickly do what you want to do and come back. Okay, this is what we call the inspiratory reserve volume, and this is what is the functional residual capacity. This is normal, this kind of residual capacity there. But don't think that this is a dead space. Okay, this is also like it's always exchange, but this is what you will have always in storage. Like something is a water pitcher is there, you are constantly maintaining that water will always be there, but that water is being exchanged, because if it is a dead volume, then you can be lots of problems. Okay, but it can become dead volume if you lose the elasticity of your lungs, then they are not functioning. That volume is sitting there, and then the person can be in the trouble. Okay, so these little things we need to know. Okay, and this is, well, of course, this figure was taken from the Indian Asthma Care Society. So these numbers we will try to, or these terminologies we will understand. Okay, so let's do one more thing, and okay, this is something very important. Okay, I'll give you the copy of this one. This is the test that people do, or the doctors or the physicians or chest specialists will do on something called spirometry. Okay, so in spirometry what they are plotting here is, you see here, this is the you can say the time, and here they are expiring the air. Suppose for the timing, just forget, I take a deep air, okay, and then I'm asked to expire as quickly as I can, like. So this is the normal. Let's say this is. Let's just for the moment forget about this one. You imagine that we are talking about this curve starting from this point. I take the deep air, and now I'll start. Okay, then I say. So what will happen? I'll have the peak expiratory flow rate at some point, and then the amount of the air that I'm able to exhale out with time will reduce, and there will be one peak. So that peak, and afterwards it reduces. Okay, and then again I'll take. So this is cycle of inspiration. Okay, and this is deep inspiration, and you are trying to exhale as much as you can. So now this is called flow volume loop. Okay, so this flow rate at different time, this is of the great significance to see the doctors and also see the effect of the air pollutants. Okay, what you see here, don't forget, this is the flow rate in liters per second. So the first number which we're calling it as PEFR, peak expiratory flow rate. Okay, this is a very good indicator of the person who is having asthma. Okay, and PEFR, the moment you go into the polluted area, your PEFR will reduce. Okay, that is again established. And once you have this thing, then you have this is reduced, then you need to exhale and inhale very quickly. So you feel very uncomfortable. The point number 2, okay, is the flow rate, okay, when the 25% of the total vital capacity of the air has been exhaled out at that point. Okay, so that FEF 25%. This is the point number 2. Okay, I again repeat that this is the flow rate. Don't forget, we are just talking about the flow rate at the point when 25% of the volume or the vital capacity has been exhaled out. Okay, this is the point where the 50% is exhaled out. This is the point where 75% of the air is, or the vital capacity is exhaled out. And this we are giving the number 12, but doesn't matter. Finally, when you have exhaled out everything, okay, that is your vital capacity. You recall that everything was exhaled out, so that is called the vital capacity. This is very, very important. Okay, suppose what I have plotted here is FEVR with time. So you see here the amount of FEVR is changing with time. So suppose if I integrate FER, forced expiratory rate, and which is function of time, right, as I show you. So this is function of time dt. What will this give me? At different times it will give me the volume of the air that has been exhaled out, flow rate times dt. Okay, so I can put this as, and this will give me volume, or I can call it FEV, not R, which is function of time. This is the volume, simple integration. Okay, this is also a very, very important parameter, force expirated volume. Okay, suppose when t equals to 1 second, this number FEV, we call this as FEV1. Okay, FEV1 is the amount of air, okay, or the volume of the air, if not amount, expired, okay, in 1 second in this spirometry operation, not the normal, not during the tidal thing, okay, but when I am running through this spirometry. So this kind of graph which we are trying to show here has essentially been plotted here. That's called volume time curve. Okay, that's what we call as a volume time curve. So the same thing what I'm telling you is also the machine or the equipment which you are using will produce this kind of graph for you. Okay. So here now I am having the units as time and the volume. You are measuring the volume onto this side, okay, and the time. And basically what you are really doing is you have this function which you are integrating, right. So if I have to find out what is my FEV1, FEV1, so I should go at 1 second, okay, plot this one and look at this one, right, clear? No problem with that. So I can also find out the other parameters like FV1, FV2, FV.75, but from this thing is an important parameter. I'll show you how to assess air pollution effects on lungs. One of the important things. There are many other things which people do. So that you can see here. And you can, this is the 11, that is the FV3 if you see here, 11. And then if you go here, this is also FV3. This is in 3 seconds, how much of the volume, okay. And finally the last thing, because the whole operation is over in about 5 seconds or so. This is the last total volume that will expire. That will be force vital capacity. But from the air pollution point of view, and the doctors have lots of meaning of this one, is that you have the two parameters which are important, FEV1, okay, that is the amount of the volume which is expired in 1 second, and the force vital capacity. That decides as to what the conditions of the lungs are generally from the air pollution point of view. So that you should understand. Don't worry, I'll pass on everything. And the third thing, of course, is a PEFR. Okay, these three things are. These other things are from the medical point of view. They have a lot of analysis they do with this one, and in children things are a little different and things like that. But from the air pollution point of view, these three things are good indicator of the air pollution. Okay, this is what is the machine. This is generally used for the peak expiratory flow rate. Very simple, ordinary machine. Okay, no moving parts, no motor, nothing is required. But with spirometry is a little complicated thing actually. So this will require, that you attach a computer and things like that. So what we might do right now is before, or maybe I should go one step further before we go. What is their significance when it comes to the air pollution? Peak expiratory flow rate that we defined, FE1 is the force expiratory volume in 1 second. Force vital capacity. What is the importance of the PEFR? PEFR is an indicator also to some extent about the asthma. Troublesome breathing due to inflammation and the constriction airways. Okay, your airways are kind of constricted. If I take the section of the airways here, okay, which looks like this, but somehow they are constricted. Okay, that shows this thing. So this PEFR value, it depends on to a person, his male, female, body weight, height, and the ethnic origin, for example. So for those people, as you are from North India, it could be different, from South India it could be different, and so these PEFR values, then for healthy people it is defined, okay, which is there, all software, it tells you that what should be the value, what a kind of person you are. So when we do this spirometry, we also need to, in addition, we do the weight and height, and they'll ask you the age, of course, and the sex, and they will also ask you which part of the country you come from, or which part of the world you can come from. So for that, they will have a standard value. If the value what you come up with, suppose it is less than 80% of the value which you should have, it means you are likely to be having the asthma, or the problem is about to begin. Okay, and lower value suggests the aggravation of the asthma and things like that. Okay, and asthma is not quite air pollution problem, but it can, once you suffer from asthma, it can trigger if you are exposed suddenly to a large air pollution area. Okay, there is some data which we didn't want to show in the beginning, which percentage change in the mortality. Okay, I mean this is normally, this is the 0 is the normal death rate, people will die and things like that. But what is the change because of the particulate matter pollution? It is some of the acute exposure studies, percentage change of 10 micron per meter cube of the PM10. Okay, this is some study by the Pop and Dockery. So that's a mortality change could be so much, morbidity change could be so much. So it could be symptoms that you can say. Reduction, this will be the reduction percentage change. Okay, this will reduction in FE1 could be so much, reduction in PFR could be so much. You see the differences that you see. So these are indicator of the air pollution, and you should have some idea, if not, not like to the idea that the doctors need to have. Okay. And I want to define two things to you: restrictive lung disease and obstructive lung disease. Okay. They're unable to get the air out, that is called as the obstruction. Okay. And most of the air pollution diseases are in the category of COPD. Okay. What COPD stands for? Chronic obstructive pulmonary diseases. Okay. And the indicator for them is that if the ratio of FE1 to FVC, okay, both are in what units? Volume? Liter, or the units are volume. So the ratio will be unitless. If this is less than 70%, okay, then which will be higher, FE1 or FVC? FVC will be higher. This is total force vital capacity, and this is the amount of the air exhaled in 1 second. So that is much smaller than the total volume that is there. So if this becomes much smaller than 70%, then the person is suffering from COPD. And COPD are generally the obstructive diseases are more attributed to air pollution. And immediately the person who is smoking, he will immediately show this one. Okay. So either you smoke cigarette or you be in the polluted area, that COPD will quickly be seen. Lower the ratio versus the obstruction. The restricted diseases, that is the problem to get the air out, air in, sorry. The low FVC, okay, the normal or elevated, then you look at the ratio FE1 to FVC, but then what you are finding here is FVC is the lower value, and the low total lung capacity that is there. So what I would like to do before I go on to something else is that we have the instrument called spirometry. It's a very expensive instrument. The little thing is about 1.4 lakhs. Okay, and then of course we need to attach it to the computer and things like that. So what I will ask, okay, let me also show you this graph. That's very important. This is again taken from the Center for Disease Control and Prevention. This is adjusted values. Okay, see, for coronary heart diseases, this is data from 1999. Okay, and this is the period from 1965 to 1919. The way these studies have been done for this period. Okay, many people die. I'm not saying that people don't die because of coronary heart disease, because generally the death rate or mortality is decreasing because of better health facilities and better education to the people, and that there is a decrease in the coronary heart disease. So is in the stroke. Okay, and then other vascular diseases, well, it's kind of stable. But look at the COPD. Okay, it's not that the people have started smoking more cigarette, or more people have become, they start smoking the cigarette, or they're starting, or more people are starting and people are smoking more and more. No, that is not the issue. So generally, this is what was the point they found. So you see that how important I'm not talking about number of deaths. Don't misunderstand that I'm talking about the number of deaths. The cause of death is this. We are saying the increase, okay, compared from 1965 to 1980, so their COPD is at rise. So this can be attributed largely either to smoking or to the air pollution issues. So this is on the rise. Okay. So what we want to do is, hopefully we should be able to demonstrate to you the spirometry test, so that you can really get a feel of this one. So either you volunteer, this is all disinfected, and this is a brand new thing. If you want to try, someone just try, but don't try if you're a smoker. Then you'll be a little disappointed and things like that. Somebody wants to try? It's a normal thing, you know, like. Do you want to try? Come. It's absolutely. Actually, this is a little for the children. We cannot do it because children, they don't cooperate so much. So, what you have to do is normal operation, and take the breath as much as you can, and forcefully as much as you can force it out. Okay, but we have to have Naresh, we should have the software for this one, isn't it? So okay, what do I do? It's not my computer, so I always have a little difficulty. So you have to open this. So you give all the inputs in terms of the various things. Suppose name of the person. Then you put is from North India, and then of course the date and time, year, height, weight, and then you can also give the smoker or non-smoker and things like that. And then that we all set. So normal operation, and then forcefully and go to the last moment you can exhale out everything, because you want to go to the last level of the residual volume that you may have. Try. First normal, like I'll do it there. Okay. And then doctors also, what they will do is that they'll put the drug. They'll do before the drug and after the drug and see the improvement. But now you try. I think maybe you want to hold it like this. Okay.
Okay, sir.
You have to put it inside.
Okay, sir.
This one. It has to be all the way like this.
Okay.
And you can't put your finger here. So we start then. Second. Okay. I think you need some training. Naresh, why don't you do it? That's much better. Let Naresh do one time, and then we can repeat the things. So कोई बात नहीं उसमें क्या होगा. See how this is really done. Wait. We normally put the this thing here. Okay, should show there. Normal ordinary thing. Then so this was a little okay. See here, as you exhaled out, this is your flow rate as a liters per second. Okay, and this flow volume curve is coming here, and then you see here, this is what you say, this is PEFR, and at different time, and then you get the total capacity, and these are the predicted value for him. Okay, this. So obviously he has not performed so well, because he said that he's suffering from something. So normally it should be like this for his condition. So you can find out force vital capacity, okay, FV1 percentage, okay, and then PFR, that's 9.61. These are the predicted. It means for the person of his age, his height, which I mentioned here, force vital capacity should be over 4.7, FE1 should be 3.96, FEV1 percentage of the total capacity should be like this, and PFR should be this. So these are the 25, that is after the 25% of the volume is exhaled out and 50% is exhaled out. And then you see here, he could only perform the 66% of his what he should be. That is the percentage, this one. There are only 79% of this one. And this is FEV1. Okay, this is 119.3 percentage. Okay, and this is how you can find out. And in fact, what this is done this is done, I mean, we have to get the best results. So this for the same person has done twice or thrice, and then out of 3 times, whatever the best results are there, that is taken. So you can record the things, and then you can see how the people are performing in terms of the, what we as air pollution people, we normally want to see this and PEFR, 3 things. Okay, so especially in PEFR, peak expiratory flow, okay, the performance was not very good. You see here, what was expected was at some point somewhere here, okay, and it performed here. So this is only about 50% of the, suppose this is 6, so he should be there about here, okay. So that is how you can really measure it, you can really see the things. Of course, normally this is done by the doctors, but the data, or most of the time data, are used and analyzed by the air pollution people. Okay, so this part we'll leave there because that's all I wanted to demonstrate to you. But we do this thing 3 times, you know, so, and the best results are taken. Okay, so I'll show you some of the work which was done. So so you can get the real feel and real numbers, you know, like master student, okay, he went on to do the measurements of the pollution levels at 3 different locations, okay, and he kind of involved some people for the measurements of spirometry at these 3 locations, okay, and analyze the data. 3 locations are Vikas Nagar, this is Vikas Nagar, IIT Kanpur, and Juhi Lal Colony here. Okay, so what he did was, I've cut down many slides. He did lots of measurement, okay, for PM10 at different places, okay, and also for PM2.5, okay, that's important. So these are the IIT Kanpur was cleaner side. These are little comparatively high pollution level, as you can see here, okay, and then lots of people were involved, and then the measurements. This PEFR was done daily basis because it was very simple. Just you say, okay, flow this thing, but the spirometry is a little complicated, as you can see, okay, and then it takes a while before the spirometry. So spirometry was done in various seasons, okay, they were conducted on each individual of the cohort with the spirometry G. This is the same equipment to observe the general trend FE1, FEC, and this was done daily, okay. Okay, so based on PEFR, the people in the Juhi Lal Colony, this is the percentage of the population. This is, it means 80, like let's say here the 90%, or well, let's say about 20% of the people, their performance was as good as it should be. Okay, what you see here is the green zone is the observed PEFR was above the 80% of the predicted. Predicted value means in this concept, predicted value is the normal value, if you like. Okay, the normal performance based on age, height, sex. So that they performed, I mean, for example, the IIT Kanpur, almost like up to 90% of the people, 90% of the cohort or the group, they performed very well. Only there was something like about 15%, their performance was a little poor, between 15 to 80% of their actual value, what it should be. Okay, but as we come to the polluted area in Juhi Lal Colony and Vikas Nagar, you see their performance, the people only about 65% or 70% people perform as per their, what they should really be performing. But if you go to the more polluted area in the city, only about 20% of the people they could perform as per the expected value. Many people were in the range 50 to 80%, and there were almost some percentage, which close to 10% people were in the red zone, means they are performing even below 50%. Okay, so that is certainly that is taken as the person already suffering from asthma. Likelihood of these people will, with the pollution or whatever the reason, they could be pushed to the red zone or the problematic zone. So you can clearly see as to how the pollution and they have the effect on PEFR. But more than that was the analysis was done for the changes in the delta PEF with respect to PM10 and PM2.5. Okay, So how it was done was, what was the average change in the performance of the people, okay, as there was change in PM10. So we will not go into so much detail, but I'll show you the results if I can. See here, on 15 days at various sites they went, okay. This was the cohort site, Vikas Nagar for example, and then what you are seeing here is these are your pollution levels. Every day they are measuring, okay, and then pollution level are shown onto this side, PM10. So sometimes 300, 200, 250, 300, 400, 450 or so, and then average change, okay, in PFR of the people, okay, is plotted on this side, and then as you see here, as the pollution level goes up, there is a drop in PFR, okay, delta PF was negative, you can say, okay, there was a drop here again, okay, and the pollution level again goes up, and then you can see constantly there is a drop in there, okay, and this was the PM 2.5. It was not so apparent for PM 2.5, but the other areas you will see, okay, this is at the Juhilal colony site. So this is the pollution level, increase, decrease, very high, and then decrease, and again high, and things like that. And you see the performance, the lung function in terms of the PFR, a change in PFR. And this is average for all the people. It's not just one individual. One individual can perform anything. So here you see it's clearly seen. As the pollution level is going up, the performance is dropping for the people. As the pollution level goes up, the performance is dropping. And similarly, for PM 2.5 at Juhilal colony, that also is clearly seen. As the pollution level PM 2.5 goes up to like 150 or so, because the pollution level is high, and so the performance decreases. In fact, it becomes negative from the normal performance, okay. And then as the pollution level drops, okay, which is close to about 60, their performance improves. So PFR is related even with the daily activities, like you can improve and it can go down. So this is what was clearly seen, but it was more related with PM10 than PM 2.5, which was a little surprising, I mean. And we should also show you the results from IIT if we have. Okay, IIT performance, I mean, we didn't, because the levels were so low and the variation was also not so much, we didn't see as clear trend as we did for the other two locations. So IIT Kanpur, we could not see so much of, the correlation. One is going up, the other is going down, and things like that. But okay, then what the student did was that this delta PF, he correlated with respect to PM10, PM 2.5, and with PM10 1 day lag. Okay, they took the PF value for the next day and the PM10 value the 1 day before, and then PM 2.5, and they could see there was a correlation between delta PF and PM10, so a negative correlation. It means as the pollution level went up, the performance delta PF that decreased, okay, or the PF that decreased. So that was clear, but more related with PM10, and you will see that PM10 and PM 2.5 are expected to related. PM10, the previous day and the current day would be related, so will be PM 2.5. And PM 2.5 was highly related because PM 2.5 don't change so quickly as does the PM10. So the correlation between PM 2.5 of the today and yesterday was very high, and PM10 and PM 2.5 also correlated, and this were all significant statistically. So you can say that clearly there is a effect of air pollution onto the PFR. This is a graphical presentation how the PM10 was changing, okay, as it was increasing, the performance in terms of this thing was decreasing. So it was not so significant about PM 2.5. There was some, you can fit a model to this, and then you can say how things will change. There were 39 people those were involved, and you can see how PM10 concentration and the, it's basically the coefficient, okay, that you can compare with. Okay, the other thing which I must show you is this one about how the people performed in terms of the FEV1. Okay, what the student did was, all the people, they were there, about 30 people were there. So he plotted you see the solid spots. Okay, solid spots this is what they should actually perform based on their body weight, based on their height, based on sex, and based on which part of the country they come from. So this is what it should be. Okay, for the person. And you see immediately below this is what the people performed. Okay, so there is one-to-one correspondence for everything. Well, some people did perform better than what they should. But you see, in general, there was a likelihood, because this area was polluted. In general, the people performed much below to what their actual performance in terms of FE1 should be. Okay, so the average deviation was about 0.3 liters, which is quite high. Same thing was in the area of this is force vital capacity of the lungs. So that also you can see the solid thing is what that's what they should be. On purpose they are put in the increasing order, so that the graph is seen very clearly. So you can see here the people performing below there. For example, he should perform at this level, but he was performing at this level. For example, this person, the number 20, let's say, okay, should perform at this level, but maybe he was performing at this level. So again we can find out the mean variation from the predicted values is again 0.42. It means most of the people are performing below what it should be, and the average decrease in the vital capacity is about 0.42 liters. Okay, this same thing was in Juhilal colony, that was again polluted area, so that you can see the people performing below this thing, and 0.31 here, and again close to 0.4. Okay, and we also have the IIT data here. So IIT also, in terms of FE1, FEC, the people performed a little below, but that performance was not as bad as it was in the city. So you can see here the mean deviation of 0.13. So that was the deviation as you see here, because the graph is a little bit exploded, so you see difference is more, but it's not that much difference as because it's starting from 2 liters here. So you can see here. So was in FVC, this was about 0.27 liters or something. So it was clearly, you can establish that how the pollution will affect the people, their lung performance, and then associated lung diseases and things like that. And there are many more things people do in this kind of study, but we need to cover this particulate matter and health effects just in one lecture, so that you can see here. We'll stop there, and for some of the guesses we'll talk in the next class. We need not to be expert of the health effects, but we should know. Okay, and then obviously now we have this information, where we use this information to set the ambient air quality standards, right? That's what we want to say. Okay, we want to say, okay, the people need to, at least we want to reduce this 0.13 to, let's say, 0.13 to, let's say, 0.05. Okay, then what should be the improvement in the air quality? We can do with our studies, and this, well, all right, let's set this standard at this level. Okay, the problem was that people were insisting that we should do some studies of our own, because we all the time are trying to borrow the data from somewhere else. They say, oh well, Indian conditions are very different, the pollution levels are different. There's two arguments. One, somebody says the nutrition level is so bad, so low for the people in India, so their likelihood of poor performance, lung performance will be high. The other argument was there, well, we are acclimatized to the poor conditions, so the body response will be better, and body has acclimatized itself to perform better even under the worst conditions. So there were lots of arguments and this and that. So sometimes we need to create and develop our own medical tests and medical studies. Obviously in this work many of the medical people were involved, and this was one of the master's thesis. The student did very good job. You'll be surprised. This is what his thesis is, and it's about 30 pages of thesis. Normally we see the MTech thesis to be very long, and but the work done was very good actually. It's published in some good international journal and things like that. Okay, we'll stop there.